Okay, on to station 3. A 100-gram glass of warm milk cools from 55 down to 20. How much energy does it release to its surrounding? Guys, on these, don't forget to do your warming and cooling curve. With these warming and cooling curves, same axis labels, time and temperature. All right, and here we are starting at 55, and we're going down to 20, and it's a decrease. Okay, well, the equation for this is Q equals M times C times delta T. Heat is equal to mass times specific heat times change in temperature. Well, our mass here is 100 grams, so Q is 100 grams. Now, to find our energy constant here, we need to think, okay, this milk is at 55 degrees Celsius. Milk, kind of similar to water, so because it's at 55, it's going to be a liquid. If it was above 100, it would be a gas, boiled milk, kind of smelly. If it was below 0, it would be a solid. But because it's between 55 and 20, it's going to be a liquid. So we will use 4.18 joules per gram degrees Celsius times delta T. Delta T, remember, is our change of temperature. We started at 55, we went to 20 degrees Celsius. That means our change of temperature is 35 degrees Celsius. So times 35 degrees Celsius. Now I'm going to multiply here on my calculator. 100 times 4.18 times 35. Nice simple multiplication. Now this is, I'm just going to write, this is the number I get on my calculator. 14,630. But this is not correct in terms of the number of significant figures. How many digits are we going to get to keep in this problem? As I look here at my problem, I see, oh, this 35, it only has 2 significant figures, 2 digits. And so I'm going to keep the 1, and I'm going to keep the 4, but behind the 4 is a 6. So that 6 is going to round the 4 up to a 5, which means that my answer here is 15,000 joules. 2 significant figures in 15,000, 2 digits here that are significant. So that is my answer because this only has 2 digits that are significant as well. Number 2, 200 grams of water evaporated from a cup. How much energy did the water absorb? Hey, these ones are fun. When it's a phase change, these ones always get students tricked up on the test. Here we're evaporating. That means going from liquid to gas. When we have a phase change, the temperature is constant because all of the energy that's coming in is going to change the spacing of the particles, not the speed of the particles. So here we've got a nice flat line graph here. Again, Q equals M times C times delta T. 200 grams. All right, we're evaporating here. Am I liquid? No, I'm not liquid because I'm evaporating. Am I solid? No, I'm not. Am I melting or freezing? No, I'm not melting or freezing. Oh, look, there it is. I'm evaporating. So I'm going to use the constant 2,260 joules per gram times delta T. Wait a second. Mr. Gooden told me something about if the phase is changing, the temperature's not changing. Oh, so I'm not going to include delta T into this problem. And so I will just multiply here. 200 times 2260. I'm going to write what my calculator has. 452,000 grams cancels with grams, so my answer here is with joules. Okay. Now how many digits do I get to keep? Well, my 200 here has 3 significant figures, and so I get to keep 3. So this is going to be my final answer. There are 3 significant figures here as well. Excellent. Number 3, how much energy is transferred if 200 grams of water is heated from 25 degrees Celsius raised to 75? Time, temperature, 25, 75, raised, bam, done. Sometimes as I'm walking around, I see heating curves that are very complicated, like this. In this problem, you're not going from solid to liquid to gas and so on. It's just a very simple heating curve. This is water. It's at 25 Celsius, so it's a liquid. And it's just a liquid that's heating up. It's thermal energy that's being absorbed, or energy that's being stored as thermal energy. Okay. Mass here is 200 grams. We are a liquid because we're at 25 to 75 degrees Celsius. So we're going to use this 4.18 value, 4.18 joules per grams degrees Celsius, times delta T goes from 25 to 75, which is 50 degrees Celsius. 200 times 4.18 times 50. My calculator says this. Okay, now looking at my significant figures here, this one only has 2, so my answer can only have 2. This one has 3, this one has 3, but this one only has 2. And when we're multiplying, we get the number that has the lowest. So I need to change this to only 2 significant figures. I get the 4, I get the 1. Behind the 1 is an 8. Well, that 8's going to round the 1 up to a 2. So this becomes 42,000 joules. Number 4, heat capacity of steel. Oh look, here's our energy constant here. If you apply 4,000 joules, oh look, there's our heat to a 100 gram bar of steel that starts at 20 degrees Celsius. What would be the final temperature? Let's do our heating curve here. Temperature and time. It starts at 20 degrees Celsius. What temperature does it go to? It doesn't say on here. Does it go to 4,000? No, that's not a temperature. It's a joules. Does it go to 100? No, that's a gram. That's a mass. Does it go to 0.49? No, this is an energy constant. It's going to be our C value. We don't know what the temperature goes to. That's why it's asking, what would the final temperature be? So we know it's going up because it's being heated, but we don't know what it's going up to. So let's find out. Our Q is 4,000 joules equals, our mass is 100 grams. Our energy constant is 0.49 joules per grams degrees Celsius. Okay, check out, this is steel. That's why we can't use any of these. This is for water. All of these are for water, H2O, that's what that H2O means here. So we've got to use the energy constant they give us. Time, delta T, we don't know what our change of temperature was. We're not going to plug in the number 20 here because that wasn't our change of temperature, that's just the temperature it started at. So we're going to leave delta T here as a variable. Okay, pretty simple. I'm just now going to multiply these two numbers, 100 times 0.49. Why did I do that on a calculator? That's 49. And then grams cancels with grams here, so this is joules per degree Celsius times delta T. I just simplified these here. Still equals 4,000 joules. Okay, now I just need to find delta T. It's being multiplied here, so I'm going to need to divide both sides by 49 joules per degree Celsius. 49 joules per degree Celsius. When I divide, these will cancel out. I'll be left with Celsius. So 4,000 divided by 49 gives me, I'm going to just write what my calculator has here. Remember, this is for delta T. Delta T equals 81.632. I can't stand to write it anymore. Let's just leave it there. Okay, how many digits does this get? Well, looking through my problem here, this one has 4, this has 3, this has 2. So my answer only gets 2. So I get the 8, I get the 1, and I look behind the 1 and it's a 6. So that 1 is going to round up to a 2. So this is 82 degrees Celsius is my final answer. 2 significant figures here, 2 here, that's how I know I'm good.